Welcome to Mr. McLean's Physics 30 class, and we are exploring mechanical energy problems. So these are the problems from the mechanical energy booklet I handed out in section 12.5.4. And the first question we'll be dealing with is a swimmer going down a slide and then shooting off the end at 5 meters, flying a distance of 5 meters in 0.5 seconds. So as with all questions, let's start with a list of knowns. So knowns from the question, we have the distance the swimmer travels, which is 5.00 meters in a time of 0.500 seconds. We also know that the swimmer is at rest initially, so the initial velocity is 0 meters a second. And we want to know what is the height the slide must be. So since it's the height from which the swimmer starts, and we've already defined that location as the initial, I'm going to call this height initial, okay? Because the swimmer starts on top of the slide, has a velocity of 0 meters a second, and since I'm calling that the initial velocity, I'm going to call the height from which he starts the initial height as well, and that's 0. This means I'm also going to need to know what the final velocity is and what the final height is going to be, and we'll explore what those two are in a moment. So before we go on to do that, let's just get rid of this part here because we're done with that. And let's see what else we can sort out here. So next now let's, and of course the one known I always forget to write down that we always need to have, acceleration due to gravity is 9.8 meters per second squared. That's a constant, so it's always there. If it's not written down, you always assume it's in the question anyway until you prove acceleration is not involved. So let's take a look at what a question like this might be like. So most pool slides look something along this line, and they're built some distance above the ground. And they're built so that they don't go straight into the pool, they go some distance above the pool, so you get a little ride as you fly off the end of the slide. And in this case, the person flies off the end of the slide and into a pool some distance away. Which we'll call D, and we've already identified D as being 5 meters. And notice how the person is going to do a projectile arc, because if you think about it, they're going to come down the slide, they're going to hit this part, they're going to rocket off this way, and as soon as they come off the end, they're going to have some velocity that they picked up from going down the slide, and they're going to continue moving at that speed until they impact the water. So if gravity wasn't involved, they would just continue to move in this direction. But since we have gravity, they're going to be falling at the rate of gravity, so they're going to follow this projectile arc, and they're going to hit the water. So a key piece we need to identify, the final velocity, the final position we're interested in is not the end of the slide, it's when the person impacts the water, and the initial point is right here where they started. So using mechanical energy, which is the mechanical energy of the initial state is equal to the mechanical energy of the final state plus any external work that's going on, we can try to solve this problem. So mechanical energy is always equal to potential energy plus kinetic energy. So we'll just write these in. So now we can try to identify what aspects of this formula we need to use and which aspects we can get rid of. Now the proper full format is that you would be using mechanical energy initially equals mechanical energy final plus work external. And what we usually do is identify any kind of external work and then eliminate it in the first step to determine whether or not we need it included in the next line, which I haven't done here as I want to explain the whole process. So really, as long as you memorize one of these two forms, you can solve any kind of mechanical energy problem. And when dealing with mechanical energy problems, you want to keep a framework to help you identify what parts do you need and which parts do you not need, and one of these two will help you. This is the one, mechanical energy initial equals mechanical energy final, is the one in my head because I know mechanical energy is equal to potential energy plus kinetic energy. So knowing this, I can get to this line. If you have trouble understanding the relationship between these two, then especially make sure to memorize and learn this formula and use that in all of the instances. So now let's apply a little physics knowledge and see if we can't figure out if there's any parts of that expression we can get rid of. So we know that the rider, the swimmer, is starting from rest at some height. So in the initial state, they're going to have a height, and so potential energy is going to have to stay. And if you don't understand why, make sure to read the booklet, and I'll also show you again here in a moment why. But the key piece that tells us is that kinetic energy is going to go to zero. They have no velocity left or right initially, so that term goes to zero. Then, when they get to the bottom and they fly off and they hit the pool, their height goes to zero. They'll have some velocity still that they picked up from accelerating down the slide, but their height will be zero. So the potential energy term goes to zero. And aside, we're going to assume that the little hand push off to get them started, let's say that equaled the same amount of energy that was lost due to friction, because the question doesn't tell us anything about either of those two cases, and that'll let us just say that the whole thing goes to zero here. So there's no external work, so we're just going to say this person slid down the slide due to the height, right? Slide's slippery, so they slipped down because they're higher than ground, and when they got to the ground, they had some velocity due to the energy from being at some high height and coming all the way down to zero. So now let's plug in the variables for potential energy and kinetic energy and see what that gets us. So now we're left with mass times gravity times height, and this is the height in the initial case because I'm talking about the potential energy in the initial situation, and that's going to be equal to 1/2 mass times volume squared, sorry, not volume, velocity squared, and that's the final velocity. Now here, we now have two unknowns. We don't know what the height of this object is, and we don't know what the velocity is at the end. And we also don't know the mass of the swimmer. The mass of the swimmer is an easy enough one to work out. We can factor that out. So we will have the mass times gravity times height in the initial situation is equal to mass times 1/2 V final squared. So I have the mass, it's the same. The swimmer is not going to change mass going down the slide. So since mass is the same on both sides, if we just divide by mass, I don't need to know what the number is, but we know that it'll cancel. And that leaves me with acceleration due to gravity is equal to height in the initial situation times 1/2 velocity squared. So now let's just do a little aside. Let's see if we can figure out some more of the unknowns we're dealing with. So the height is the issue that the question wants us to solve. G is just 9.8 meters per second squared. 1/2 came from the formula, so the other unknown we have at the moment is the velocity. And the velocity is going to be the left to right velocity as we're moving at this point right here. And a way to remember which velocity you need to have is to think about how potential energy is concerned with the y direction or the vertical. So kinetic energy is interested in the horizontal. We're dealing with the two different axes through potential energy and kinetic energy. Therefore, we only care about the velocity in the horizontal direction. And because the question gave us the distance and it gave us the time, we can figure this out. And it doesn't tell us anything about an acceleration. And since the last time a force was applied on the swimmer was when they came off the swimming, like came off the slide, then it's a constant velocity, so you can use d equals v times t. So the distance in this case is 5.00 meters, and that's going to be 0.500 seconds times some velocity. Divide both sides by 0.500 seconds, and you'll wind up with 10.0 meters per second squared. and that's going to be our final velocity, which we can plug in to there. So now if we plug in all the things we know, we'll wind up with an expression like this. So if you multiply this through, it's going to be 10.0 times 10.0, so 100 meters squared per second squared. Multiply that by a half, and you'll wind up with 50.0 meters squared per second squared, because you got to remember your units as well. Now over here, 9.8 meters per second squared times h in the initial situation. So I want to know what h is, so we're going to divide by 9.8 meters per second squared. And if you're trying to follow your units, it's important to make sure that you had squared your units as well. Otherwise, you're not going to get the correct units over here. So now I've got per second squared on both the top and bottom, but I have a meter squared on top here and a meter here. So that means my answer is going to be left in meters. And in this case, the answer is 5.1 meters. So this slide would have to be a height of 5.1 meters in order to have the swimmer shoot 5 meters off the end of the slide and do so in a time of half a second. So that's what we do with those questions. I hope that was insightful. If the video went a little too fast, remember just rewind it or start it from the beginning and go through it again. And if that made sense and you're ready for the next question, I'll see you in video 2.